really how to incorporate accuracy standards. A lot of people sometimes take it lightly, but many educated user they feel the importance of adopting accuracy standard when dealing with geospatial data. So my agenda, more or less, will revolve around these. We'll talk about accuracy and error, source of error in our business and our geospatial data, some statistical concept, because a lot of people confuse about this simple concept, but it overwhelmed a lot of people here. And we'll talk about the mapping standard in the United States, which is really ASPRS standard mainly now. And we'll talk about the latest edition, the greatest in it, and what we changed lately. And how we perform horizontal vertical accuracy in case you're not familiar with the process. And I will bring one or two example. And if we have time for a question and answer. So let's talk about accuracy. Accuracy is really how close you are from a true value. For whether you measure something, try to observe something on a map and the ground. We doing with this mapping or surveying, trying to reach the true value, or whether coordinates for that thing's feature or corner of a block or a house. So while we have another term is repeatability or precision, this is not really accuracy. It's just a closeness with which measurement agree with each other. If I do 100 measurement on the same thing, I will get definitely 100 different values. I mean, they change maybe a very small change, but they are different. How close these 100 measurement I did to each other, that's what we call precision or repeatability. And people confuse about accuracy and precision. We call it relative accuracy in the past, but with the new edition, we really moved away from relative accuracy because it gives the sense it is accuracy while it is not accuracy. So we call it data internal precision now. And the true value you need to have in mind, the true value is a matter of metaphysics. We will never reach it. We will never reach it no matter what we do, no matter what technology today or 100 years from now. That's beyond our ability to comprehend what's the true value of things. If I say the meter measure, for example, even NIST standard, they give you, but that's not the true value. Neither NIST nor anybody knows what it should be that true value, but we publish or reach a value close to it, and that's what all we doing in our measurement. We're trying to get to the true value. We cannot, so we just give approximation. And on the graphic, if you're not familiar with how we measure accuracy, that's if you look at an ortho, and on the left, upper left, you have the triangle, the position. If I superimpose that position from the surveyor in the field on the ortho, most of the time, if it's not all the time, this survey not gonna totally perfectly fit the position on the ortho, because ortho always has some error. So the difference between these two locations, obviously the surveyor survey the corner of that stop line, the white one. But our ortho is showing it a little bit off from the survey. The difference, that's the error we're talking about. So we'll talk about again about absolute accuracy versus the relative accuracy, which we called before. Now we call data internal precision. So on the left absolute accuracy, that's when you measure the error difference. There is value for it. How far you are from the survey value, and we assume the survey value is representative of the true value. Remember, again, we cannot reach the true value. So our surveying technique, it will give us kind of pseudo true value. So that's absolute accuracy. While on the right, what you see a LiDAR point on a flat surface, for example, and you see that's a fluctuation. All these LiDAR points supposedly to give the same elevation, but again, with the error in the laser and measurement, they never gonna give you the same elevation. So that fluctuation, that's data internal precision. That's what we call before relative accuracy, repeatability. So that's a fluctuation up and down around the mean here of that surface. That's what we call precision. So why we are concerned about accuracy? And the simple answer is all our measuring techniques are not perfect. They always have error, no matter how accurate is the technique, whether laser, whether whatever, total station, or GPS. They all have source of error. We cannot eliminate. And the error we're talking about, what we call, I will define it in the next few slides, the random error, which we can minimize, but we cannot eliminate it. We will never be able to eliminate it. So source of error, let's talk about in our geospatial product, let's talk about the product we are dealing with. You have a stereo compiled break line and vector feature, road center line, edges, houses, and things like that. That's a vector map and 3D break line. And we have the ortho rectified mosaic, and we have DSM. And the DSM, this one from imagery, but could come from LiDAR. So the source of error, you could be using the wrong data. Poor quality of a ground survey point, for example. Poor airborne GPS. Poor quality of camera and LiDAR system. Poor photogrammetric process. That's all generate error, for example. And here is a little bit more on it, more source of error. You see all these arrows going to the different stage of the process. Could be an aerial triangulation, ground survey, and the data acquisition, and the data assumption, and the product generation, whether ortho, point cloud, vector, or GIS. Those all potential errors in the data. And always inaccurate process result in inaccurate product, no matter how nice is your map. If you look at the map on the right, is a beautiful map. You have a nice break line, road edges, and sidewalks and utilities. But if it's not accurate, really doesn't mean that much at all. If you require accuracy, for example. So what does it take for us to do it right, to do it accurately? Really, two main things. You need some people working on the process, have some knowledge about the process, whether photogrammetry, GIS, mapping. You need some fundamental basic knowledge. You can't just bring somebody from anywhere and give him a workstation to produce maps, for example. That's taken. The other things, when you talk about accuracy and precision, which we're going to talk a lot about, you really need somebody have sense of a high level statistic and some math, because a lot of people think those topics way above their head. And that's a problem, because once they have that assumption, they could push a product out the door without knowing is good or bad. So you really need to be aware in your education or your team education. You need to have these fundamental knowledge to do it right. So now I mentioned earlier random error, systematic error. A random error, that's the error exist in any measurement, right? And we cannot eliminate it. Because that's our nature, a human nature. And like I said, this is related to the true value, which is metaphysics for us. But you can reduce the random error. I use a better technique. I can be more careful. I can repeat it multiple times. Those all best practice to reduce the random error, but you will never be able to eliminate it. On the other hand, we have another error called systematic error. That's an error which follow a certain model, mathematical model or geometry. And that's the one we can model, calculate, figure out, and remove. So random error you can minimize, you cannot remove. Systematic error we can model or remove. And this is just an example here. If I have four score for target shooter, for example, A, B, C, and I will see if I look at A, I would say this shooter is accurate but not precise. While B, I will describe it as a precise but not accurate. C, it is accurate and precise. And D is neither accurate nor precise. Why I said A is accurate, not precise? Because the shooter brought all these shots around the bullseye. The problem with it is scattered. That means the repeatability is not good, the precision is not good. So he or she was accurate to target the bullseyes and stay around it, but those shots are a little bit far away. While B, you see how close these shots, the repeatability is good. He or she always hit in the same place, but that same place is not the bullseye. So it is not accurate, but precise. While C, they were accurate and precise. That's what you want in your data before you deliver it to the client. You want it accurate and precise, and D, you don't want to deal with that because it will put you out of business very soon if you deliver data not accurate and not precise. So if you look at B, the shooter is a sharp shooter, definitely. But he or she has a bias of 7 centimeter in this case off the bullseye. And that's not because they're shooting skill. That's probably because of the instrument they use. If they are using bow and arrow with cytoscope or a rifle with cytoscope, it could be the calibration of the cytoscope they are using. They targeting the bullseye, but the cytoscope taking him or her to the 7 centimeter away. Once that calibration of the cytoscope or the rifle barrel, for example, once that fixed mechanically, the result of the shooter in B will be identical to the result of the shooter in C, accurate and precise. So the ASPRS standard, historically, we use the root mean square error. We don't use the standard deviation or sigma. And that's how you calculate the root mean square error. You find all the error in the individual measurement, and then you square it, and you divide it over the number of these measurements, and you take the square root of that, and that's the RMSE. So the RMSE, the root mean square error, is approximately equal to standard deviation plus bias. So if we don't have a bias in the data, RMSE and standard deviation will almost exactly going to be the same, by the way, which it doesn't really matter whether you use RMSE or standard deviation. But the problem, knowing we always have the potential of the existence of systematic error, you want to stay away from standard deviation to measure your accuracy. And I'm going to show you in a couple examples in the coming slide. So the root mean square error include random and systematic error, if it exists. More useful to use at it reveal biases systematic error, and it tells us how accurate is the data, while the standard deviation includes only random error, reflect only how precise is the data, the repeatability of the data. It does not tell us how accurate is the data in the presence of biases. It only tells us how precise is the data. And this is a good example to show you. So if you look at both cases, the left and right, they both give you standard deviation of 3 centimeter, which is thus, if I measure my accuracy using standard deviation, the problematic data set on the left, it has bias. The standard deviation will not pick on that, definitely. So while I have the root mean square error, if I calculate for both set, the left data set will give me 10 centimeter. The right set will give me 3 centimeters, similar standard deviation because there is no systematic error. So if I base my conclusion on acceptance or rejection of the data on the right, for example, on a standard deviation or RMSE, is no problem, right? No systematic error. But if I base my conclusion on the left data set based only on standard deviation, 3 centimeter, and I supposed to meet 5 centimeter, for example, I will push it out to the door. I will think it is passing the requirement, accuracy requirement. While if I look at the root mean square error, it will tell me the data is failing to meet the project specification of size centimeter. So that's the difference. I hope you understand that and appreciate. And we always dealing with the normal distribution curve, right? I mean, this is the essence of all our work when we deal with accuracy. Data always need to be vary around the average, with most value being closer to the average. So we want that bell curve very narrow around the average as much as you can. You don't want it to spread the tails wide because that's where the precision will be example for it. And you see, like you have the RMSE around 68.2 within +1, and 95 is to the RMSE. That's the what you see it in the dark blue. That's what we talking about with the ASPRS standard here. We measure the accuracy in that area under the curve here. So the common error estimation terms, you see, like you're familiar from whether high school or college, I'm sure you took some statistic about most probable value, standard error, 90% error, 95 error, and 3 sigma, and surveying, for example, and blender rejection. Those are just different way to represent the same accuracy using different confidence level. And that's how the factor why it is 2.147 times the standard error, for example. So if I take a data set and I test the accuracy and I get a standard error of 10 centimeter in the easting and northing horizontal, and also 10 centimeter in the vertical, for example. If I represented in these above table some of the value, the most probable error, if I represent accuracy as a most probable error, it will be 11.77. If I say 90%, it will be 21.4. If I represent it as 95 confidence level, it will be 24.47. So you see this number 11, 21, and 24 centimeter, they all the same accuracy. The same accuracy measure just is expressed in different confidence level. But what is this is very confusing for the layperson. Like I said, people get intimidated when they deal with a statistic and you expose them to this. And that's very dangerous in our business for a technician doesn't understand those, for example, or a project manager, for example. So what do we do? We need a new approach in teaching accuracy and statistics. We definitely need to. We need to simplify it to the layperson. And lately, I'm thinking about maybe to bring it closer for people understanding. If I use the funnel approach, and I have balls of different diameter size, for example, each one represent that confidence level, the 97%, 95, 90, and it might make people think or digest it better than what we had before. So for somebody not knowing what it means, and you present that, what accuracy you should pick. If I present you with 30 centimeter, 19 centimeter, 16 centimeter, or 6 centimeter. So data producer, they will jump, if they don't know what it means, they will jump to the 30 centimeter because they think this leave a lot of leeway for them, is a loose accuracy, 30 centimeter. While end user of the data, the client, will jump to the 6.7, while it is the same accuracy, the 6.7 and 30 centimeter, it's the same accuracy represented or expressed in different confidence level. And that's the problem we need to solve, so people don't fall in the trap of delivering the wrong data, for example. Here's another way, the same concept, or accuracy funnels, for example. If I look at the very far left, that the neck of that funnel is only 6.74, and that's the confidence level we based it on, right? But you're not required for all these balls to pass through it. It's only 50% of these balls have to pass through. While a loser by a tube of that funnel, 16.49, it is looser, but you require like 90% of these error balls to pass through it, and so on. When you go to the 30 centimeter, it's very loose, very big tube, but almost 98% of all the error had to fall within that. So hopefully we can succeed in explaining these concepts in a different ways than we taught it in the past. So let's talk about our accuracy standard as ASPRS Positional Accuracy Standard for Digital Geospatial Data. The latest one, which is we publish in the recent year to make it suitable for digital era of geospatial, when LiDAR and digital camera, was really edition 1 we published in 2014. That's the first standard in the world solely published for the digital workflow and digital product from LiDAR and digital camera. And we follow it last year. We produced edition 2, version 1, and this year in June, we published the latest and the greatest, which is the edition 2, version 2. And those that just give a credit for the team work on it. This is the main working group here, 5 of us. spent about a year and a half, I think, on this one, on the latest one. And we have a lot of people, as you see, the contributor to the addenda. We have 6 addenda, we'll talk about it. We have a lot of people from academia, government, industry, and so on. So the new standard highlight, sensor agnostic, data driven. We remove any threshold related to scale or GSD or flying altitude or certain camera format, just because it doesn't make sense. The user of the data, all they care about the data in their hand. I don't care about if you produce it using good LiDAR, intermediate LiDAR, cheap LiDAR. If that data meet my requirement, accuracy and quality, that's all I care about. Same thing with imagery, for example. I don't care whether you flew it at 100 feet or 1,000 feet, for example. If you can achieve the accuracy from what you use, that's what it matters. So that's what mean sensor agnostic, data driven. It is all metric. And we added additional accuracy measure, aerial triangulation measure accuracy, ground control accuracy, seam line for the ortho, LiDAR relative swath to swath, recommended minimum nominal pulse density, horizontal accuracy of elevation data, delineation of low confidence area, and number and spatial distribution of QA/QC checkpoint. And we introduced in the latest one a total of 6 addenda, which is one of for general practice and guideline, and we have one for field surveying and ground control and checkpoint, one map and one for mapping with photogrammetry, addendum on mapping with LiDAR, addendum on mapping with UAS, and addendum mapping with oblique imagery. And factoring in, well, that's the big things we moved now to, is factoring in the accuracy of the survey checkpoint. We'll talk more about it soon. So the nice thing about this standard, we really designed it to be simple for the user, because knowing that some users don't have the technical breadth about understanding all the accuracy and the product and the factors impacting the accuracy, they don't really know that much when they negotiate workflow, for example. So we design it for the user to say, I need accuracy of such and such. That's all they really need. I need LiDAR point accurate to 10 centimeter. That's all they really need to. And maybe if they want density, they can say at 20 points per square meter. And once you do that, the standard will set up the foundation for what is required, what requirements the vendors need to meet that accuracy. So it will set up for them the GCP accuracy, aerial triangulation accuracy, checkpoint accuracy, and it will provide formal reporting statements. So the highlight of the new standard, here is the horizontal accuracy standards. Very simple, unlimited accuracy. If your project require 5 millimeter accuracy, you can say, I want horizontal accuracy class of 5 millimeter or 0.5 centimeter according to ASPRS standard. Once you say that, that means the absolute accuracy horizontal will be that number, whatever, 5 millimeter or half centimeter, and the ortho mosaic will be set up as twice as much. Vertical accuracy, similar, unlimited vertical accuracy. And that's you see like and that's important because you have now you have terrestrial LiDAR can scan in sub-centimeter, millimeters level accuracy, and we have satellite, for example. and meters accuracy. So the standard can fit all that, really, there's no limitation. The only difference in the vertical standard, we have two category of vertical accuracy, the non-vegetated vertical accuracy, well, that's the bare earth, the open ground, and the vegetated vertical accuracy, that's anything under vegetation, whether a tree, shrubs, bushes, we don't differentiate. If it's vegetation and people cannot see the ground, whether operator or even LiDAR cannot see the full ground open, then that's vegetated vertical accuracy. And we have the data internal precision for LiDAR, swath to swath, smooth surface, non-vegetated, all these really mainly related to we don't use it in photogrammetry, but mainly is for the LiDAR. And we added three-dimensional accuracy. And also as unlimited, very simple, I need the three-dimensional accuracy of 5 centimeter class according to ASPRS, and that will set the RMSE 3D in 5 centimeter. Aerial triangulation accuracy, we have this measure. So we adopted the concept of if you produce a product and you use controlling agent to produce that product, that controlling agent has to be twice more accurate than the produced product, whether in a production or checking the accuracy, to make it simple on the user, because in edition one we have 3 times and 4 times for photogrammetry, and it's confusing and too restrictive. While now we simplify it, the aerial triangulation accuracy has to be twice more accurate than the product we generated from that aerial triangulation, whether ortho or digital elevation model, for example. And if you generating only planimetric maps, two-dimensional, the vertical you see on top really equal the vertical of the map, for example, or the horizontal of the map, just because in the ortho rectification, the effect of the DSM is not one-to-one. So that's why the elevation, we ease it up a little bit. But if you are producing ortho and elevation data from that aerial triangulation, then the twice as much apply to the horizontal and vertical from the map. A ground control, the same concept. If we are generating only ortho, the ground control has to be twice more accurate than the map. And same thing if you're generating ortho and elevation data, both horizontal and vertical, accuracy of the ground control has to be twice as much as the generated map or digital elevation model. Checkpoint, follow the same rule, 2 times. If you are QCing horizontal map, the horizontal accuracy of the checkpoint has to be twice more accurate. If you are checking elevation data, the vertical accuracy of the checkpoint has to be twice more accurate than the product you are checking. LiDAR, the same thing. Always you use it twice as accurate, whether a checkpoint or control point for the bore sighting and calibration of the data. And we added the measure for horizontal accuracy of elevation data. We didn't really have any guidance before in the old standards. So here we're saying for photogrammetric elevation data, the horizontal accuracy will follow really the ortho accuracy or the planimetric map, for example. Whatever requirement, it will follow that. So very simple approach because they both produce from the same aerial triangulation. For LiDAR elevation data, we introduce a new formula, which is a function of the accuracy of the GNSS, accuracy of the IMU, roll and pitch, separated from accuracy of the heading and the flying altitude. Those are the three main contributor to the error budget in LiDAR because laser ranging is really accurate. I mean, it doesn't add, but the positioning and orientation and the flying altitude, that the main contributor to the error of the LiDAR horizontal accuracy. We'll talk a little bit about accuracy reporting. We have we provided two set of formal reporting, one to be used by the end user or their consultant who are evaluating or assessing the accuracy on their behalf, and the other set is by data producer. So if you look at the reporting according to by the data user or their consultant, it will read this data set was tested to meet ASPRS positional accuracy standard for digital geospatial data edition 2. This is the older one, 2023, but if you're doing it according to the latest one, will be 24 for 5 centimeter or 30 centimeter RMSE horizontal accuracy class. The tested horizontal positional accuracy was found to be this much. So the statement is declaring this data is supposed to meet this accuracy, but the actual accuracy we found it to be meeting is this much. So that's and same thing for the vertical and the three-dimensional accuracy, for example. But that's, if you notice there on top, we say if the user or data producer use 30 checkpoints to verify the accuracy, because that's the minimum requirement according to the new standard. You need at least 30 checkpoints. But if the user cannot afford to use 30 points, especially for light drones project, very small project, 100 acre, 200 acre, people complain we cannot afford to survey 30 checkpoints beside the control point they need to calibrate the data. So what we gonna do? They want us to reduce the number. So we could not really reduce the number because we adopted the central limit theorem. And this is very well respected statistical theorem and well known. So according to that theorem, say you need at least 30 for the mean to be normally distributed. So, but what we give them relief, okay, if you're not going to do it with 30 checkpoint, we would rather you do it with 15 point than not doing it at all, the assessment. But if you do it with less than 30 point, you report your accuracy according to this. So say this data set was tested as required by ASPRS positional accuracy standard of this, although the standard calls for a minimum of 30 checkpoints. This test was performed using only 15 checkpoints. This data set was produced to meet, and so on. So as declaration, as a truth in reporting, instead of pushing them to lie about it or hide it, we're giving them a formal forum to say, okay, I couldn't afford 30 point, although I supposed to do it with 30 point according to SPRS standard, but I use only 17 checkpoint, for example. And from that, here is my result. Data producer statement is very simple because usually data producer, they don't have the privilege of having independent checkpoint. They usually use the same control points they use in earth angulation on the or the LiDAR bore sighting, for example, to check their final product. And that's not is a bias test, right, for accuracy because it's not independent checkpoint. So all they say, this data set was produced to meet ASPRS accuracy standard. This for 10 centimeter horizontal positional accuracy class. That's all they need to declare, and so people can put it in the metadata. LiDAR is the same vertical use, so for the new standard with LiDAR, because really it was in our mind to develop the standard to accommodate the LiDAR anyway. So you see the vertical standard is the same thing here, but you have the difference here. We have a formula for to calculate the horizontal accuracy for elevation data. And how to determine horizontal accuracy of LiDAR? There is two ways, our suggestion. Although, because it is hard to verify the horizontal accuracy in the field, like vertical points, checkpoint, for example. So people, all these years, since we moved to LiDAR in the last 20, 25 years, people don't focus on the horizontal accuracy of LiDAR, totally ignored. And people don't know what is the accuracy actually, but I think we need to pay attention to it. So you either go and follow the manufacturer specification. All manufacturer in their spreadsheet, when you design a mission, they give you predicted accuracy, vertical or horizontal. You can use that or use ASPRS standard. This is very accurate formula. We checked it with the tools used by two of the main manufacturer is almost identical with all their modeling and things like that of error. So it is a reliable formula. So you can use either way to express the horizontal or predicted horizontal accuracy. So I will highlight the major changes we did in addition to over these years. We ease the accuracy requirement for ground control, like I mentioned it. We made it twice as more accurate. It used to be 3 here and 4 times here, but we just across the standard we use the measure of 2 times more accurate, whether vertical, horizontal, whether control point or checkpoint. If you are testing accuracy, your testing agent, the checkpoint has to be twice more accurate than the product. If you are producing a product, the control points you're using in the production of the product has to be twice. And it's very, very simple that way. The other change is factoring in the accuracy of the survey checkpoint when computing a product accuracy. And okay, let me elaborate on this. All these years since we started mapping, what 100 years ago, from after World War II, maybe one, and until now, until a year, 2 years ago, in our geospatial business, we always deal with the surveyed coordinate as error-free. We don't question the surveyor how accurate his coordinate, and we take it as zero error. And we base our accuracy of LiDAR, of photogrammetry, based on this assumption. While this is not true, right? Because the surveyor could be doing a lousy job in the field, could be using a lousy technology, for example. And so we need to question it. We need to know how accurate is this data set he give us or she give us, for example. That's one reason. The other reason, really, when we started 78 years ago, our product were not accurate at all. If you're familiar with the DOQQ, which is the first digital production of map on ortho, the accuracy, the horizontal accuracy of the DOQQ was 32 feet. So if the surveyor come from the field and he give me accuracy of 5 centimeter, who cares about incorporating these 5 centimeter to the 32 feet? So we ignored it with time, but with the time passing, we become numb to that fact, right? I mean, our accuracy start improving from 32 feet to now LiDAR giving us 2 or 3 centimeter from aerial LiDAR, 3 or 4 centimeter, for example. So while if you look at our RTK survey technique, the best can give us 2 centimeter vertical, for example. And we using that to verify accuracy of mobile LiDAR, accurate to 1 centimeter or better, for example. Or even UAS LiDAR now, accurate to 1 to 2 centimeter. All these products now, more accurate than the survey of the RTK survey we use to verify the accuracy of this product. It doesn't make sense, right? I mean, you cannot verify accuracy of a product using an agent less accurate than the accuracy of the product. It's not reliable at all. So here, hopefully this graphic will illustrate it about how we doing it and what we need to do. If you look at the blue mesh, that represent our maps, whether LiDAR, whether ortho, that's the blue mesh. If you look at the green mesh, that was the checkpoint of the ground control given to us by the surveyor as they try to survey the datum. The datum is the green mesh, and that's what I called earlier the true value. Remember, the true value, we cannot reach it, we cannot comprehend it. So the surveyor with the best technique they have, they trying to approximate the datum, the true value, to their best ability by giving us what I call pseudo datum, which is the green mesh. But that green mesh has error, which is the difference between the true value and the green mesh, the pseudo datum. That's the capability of the technique they use, whether total station, whether RTK. So that's the one we've been ignoring. We consider this ACC survey datum between the green mesh and solid green. We consider this one zero in the past, always zero. So how we check our accuracy? We compare the blue mesh to the green mesh, to the checkpoint, and we calculate the ACC mapping datum, like you see in the formula down below. The ACC to the true datum, we consider it the ACC of mapping datum, and that's how we measure the accuracy. Only in this element, the upper element of the accuracy, ignoring the lower one. If you look on the right, I give you maybe another way to understand it in the vector forms. So you see, like, if this is my position A triple dot on the map, I compare it to the checkpoint, and that I express my accuracy as this, while I'm ignoring how far is the survey position from the true position. This which we assume zero, which is not zero now, definitely. So you found, instead of expressing the accuracy from A triple A triple dot to A dot, this one of the side of the triangle, we use only this side of the triangle, which is not representative. And so how we gonna calculate it now? Requirement in ASPRS sender. The real accuracy will be the mapping to the mapping datum, which is the old way we did it, which is this part, plus this part, the survey datum, which is the difference between the pseudo datum and the true datum under the square root. But I don't want people to jump. Oh, we're gonna add 2 centimeters to the our accuracy now from the RTK survey. So if I'm doing 3 centimeter product LiDAR accuracy, I will add 2, will make it really bad. It looks bad. It's not that way, by the way, because it's not uh, arithmetic addition. You just not add it. What you see the formula here, you square that error of the RTK, the 2 centimeter, you square it, you add it to the other one, and you take the square root. So the effect get really minimized a lot. So if we are dealing with a quality level 2 or 1 UHGS LiDAR, the 2 centimeter in the survey really costing us only 0.2 centimeter in the total final accuracy of the product. But the problem is if your accuracy is not a quality level 1 quality level, if you are dealing with mobile mapping, for example, and the accuracy of mobile mapping 1.5 centimeter, then you're gonna find these 2 centimeter, it will represent 80% or 100% of the product accuracy. It will add a lot, definitely. The problem we going to see now when we require this number, which is the survey accuracy, we thought that's straightforward. We can get it from the surveyor. That's wrong. The surveyor not aware what is their accuracy, neither how to get it, by the way. You would think the surveyor, and I'm not mean everyone, but the majority of them, they trust their instrument manufacturer and report. And look at the report they get. Those are actual accuracy report the surveyor they get from Trimble and Leica, for example. You find it 0.001, 0.002. Those could be precision, by the way. But no way an RTK survey give you zero error. Even NGAs, listen to them, they tell you the best you can get 2 centimeters. Because all the problem we have with the modeling, definitely. So that's the problem we are facing in the industry now. We need the manufacturer of these survey instruments to give us a better measure, which is absolute accuracy measure for that survey accuracy, which it doesn't exist now. So to make up for that, in the standard, we give a table. If the manufacturer doesn't provide you with reliable accuracy measure for the survey, you can use this. So we give different type of survey technique and what is the predicted accuracy of that survey. So if your manufacturer give you these all zeros, don't use those because this is total nonsense. This is not absolute accuracy here. Use the one we suggest in the ASPRS standard. Going back to the effect of these 2 centimeter RTK, if I added, you see, like I mentioned, quality level 1, quality level 2, it's really affected by 0.2 of a centimeter, which is not a big deal. But the big deal when you go up in the accuracy, when you start reaching 1 centimeter and like 1.5 centimeter mobile LiDAR accuracy, that 2 centimeter represents 66.7% percent of the error budget. We ignored it in the past, so you cannot ignore it. You have to add it now. And if you are after 1 centimeter product accuracy, that's 2 centimeter represent 123.6% of the product error of the deliverable product. Another major change, in addition to remove the pass-fail requirement for the vegetated area here. And if you're familiar with it before, when I presented in the vertical, we have MVA and VVA. And the addition one, we have a threshold rejection or acceptance for the VVA, like 3 times RMSE, the 95 percentile. If it exceeds the 3 times the RMSE, the data will be rejected. And that causes a problem in the industry, whether for USGS or for their contractor, because the LiDAR we have 3 excellent brands manufacturer with great quality LiDAR. You find for the project on open ground, the MVA meeting the way within the specification of the project, and sometimes it fails in the vegetation. Then what you do, whether you are GS or the contractor, you go, you refly the county or the state because it fell under trees. So it caused a problem. So, and looking at the problem with LiDAR, for example, and surveying under vegetation is problematic, because if you look at our surveying technique, people using RTK under trees, and this is not reliable, definitely, because you have the multipath, you have the obstruction of the satellite, so you don't get a good GPS under tree. And the other reason, if you look at the profile of this in the middle of the screen of the LiDAR penetration under trees, is not the full density in the bare earth, because LiDAR doesn't penetrate trees. It takes advantage of the void and gaps in the foliage. If it is good gaps, they go to the ground. If it's not, get obscured. So you survey, even if your surveying technique is good under trees, and you interpolate the elevation for the ground under the trees using very sparse LiDAR data, it gives you the wrong elevation. That's why we remove that. So what is now, now we say you're required to test the VVA, but the data decision or pass-fail decision is not based on the vegetated or the VVA. It's only based on the MVA. If the MVA is passing, then the VVA will pass and will be accepted no matter what is that number, whether 30 centimeter or 70 centimeter. Another change, we revised the minimum number of checkpoint and the maximum number, for example. And the reason, like I mentioned earlier, we try to reduce the requirement for the drones community. We couldn't find scientific reason to reduce it. So we sticking to the central limit theorem, 30. But also our table, the one you see, was a sliding scale to infinity. So if you have a huge project, you might end up 3,000, 4,000 checkpoint, which is a huge amount of number of checkpoint, and it add a lot to the bottom line and the budget of the project. So we stopped at, if the project reached 10,000 square kilometer, you stop at 120, and if If the project gets bigger, you stayed with 120. And the reasoning we adopted 120 is 4 times the requirement for the central limit theorem. Central limit theorem is say minimum 30. We thought if the project has 4 times, that's good enough to give you a reasonable conclusion on the accuracy. And I talk about this one, the horizontal accuracy for LiDAR data or elevation data. And a major change also we added the 3D accuracy. So we have horizontal accuracy, vertical accuracy, three-dimensional accuracy, and we removed 95% accuracy measure because in the edition one in 2014 we kept 95 because a lot of people at the time using NSSDA, and are they familiar with 95? So we added the 95 in addition to the RMSE, but we found it very confusing for the reason I presented. Well, you have different accuracy figure as number different, but it's the same accuracy measure. So we removed it and we kept only the root mean square error. And we added great addenda, 6 addenda really is a good source for the industry on this topic. Best practices, how do I do it? It's very simple. You have a CAD software, ArcGIS Pro, MicroStation, AutoCAD. You bring your imagery, you bring your survey points, and you check for, like I showed earlier, how far is the survey point from that ortho, for example. And that's really how, and you compute a statistic for each one here. Best practices, checkpoint should not be used in calibrating the tested product. It should be totally independent checkpoint. Check data must be more accurate than the tested data, 2 times more accurate. Check data must be well distributed around the project, and check data must be valid statistical sample. At least 30 of them should be used in the assessment. So if I am for a project with ortho, the 2 times requirement for ortho with a planimetric horizontal accuracy of 20 centimeter, the checkpoint should be accurate to 10 centimeter or better, which is we don't have problem because RTK people getting 2 centimeter on regular basis for horizontal and vertical. And this number of checkpoint, I mentioned it earlier, how to evaluate accuracy with the help of survey checkpoint. The best way to evaluate accuracy to survey independent checkpoint. But also you can use what we call second generation checkpoint. Existing data, more accurate than the product you are testing, you can use it. And for example, here, I have a project where I have some survey point and I have mobile LiDAR for the same area. So instead of limiting my testing on the few survey checkpoint, I created like 5 point across the road at 25 feet interval. So I ended up creating over 540 additional checkpoints from mobile LiDAR. Mobile LiDAR was as accurate as the RTK survey. And why don't I use it for vertical verification? So that's one way you can do it. Ortho for horizontal is if you have very good accurate ortho with accuracy of the ortho twice the accuracy of the ortho you are to assess the accuracy for, I can use it. And these are great feature, for example, to extract second generation point for the testing. Intensity LiDAR, this is high density, like 30, 40 point per square meter intensity from Geiger mode. It can be used for generating horizontal accuracy for ortho, for example, because if you look at these runway detail, those corner can be used for horizontal accuracy assessment of LiDAR. Elevation data, if you have a good set of LiDAR, aerial LiDAR, mobile LiDAR, a drone LiDAR, and accurate, and you sure about its accuracy, and it is twice as much as the accuracy of the elevation data you're producing now, I can use it as control or checkpoint. And here, one example I just want to show you quickly. We did how we perform accuracy. We did the proof of concept for pen DOTs when we fly ortho imagery for them 3-inch and aerial LiDAR, and we drive our mobile LiDAR. When the drones came online, they want to see what the drones can do for their project. So they hire us to to fly with the drones section of 35 SR80 in Pennsylvania. So we use EBX RTK with SODA 3D camera, and we flew it what you see to the east of the highway and the west, because we could not at the time. Now we can fly with a new FAA regulation, but at the time we cannot fly over people, so we flew it east and west. But the SODA 3D camera is like kind of oblique camera. You can open the field of view. So we were able to have imagery overlapping over the highway. And we produce stereo brake line and digital surface model and ortho. And we created two sets of contours, one from the mobile mapping and one from the UAS. You see in the lower right corner, the two set. But when you look at them, the two contours are almost identical to each other behaviors wise. They follow in each other. But there is a shift between them, by the way. There is separation a little bit. That separation, what we call the systematic error. Remember, we talk about systematic error. If you know about it, you can pick it up. If you don't know, you always wonder why this separation between the blue contour and the red contours. And so what PennDOT did, they went after us after we delivered the data, and they surveyed 28 independent checkpoints, 14 on the northbound, 14 on the southbound, and they did their analysis on the accuracy. And look what we found here. What we found, if you know these basic statistical analysis, first thing you look at the mean or the average. The mean is an indication of biases. If the mean is high and as high as the root mean square error, this is a strong indication there is a systematic error in the data. So if you look at the standard deviation is low, half of the mean, half of the RMSE. And that's what we meant earlier. If I suppose to meet, say here, 0.1, 10 centimeter, or this feet, 1/10 of a foot, for example, and I look at the only standard deviation, this data is meeting the standard deviation of 0.1. While if you look at the root mean square error is 0.22, twice, more than twice as much. But how you analyze that, why this high? You look at the average. The average is almost as big as the root mean square error. And that's what we mean. Once you know what is your systematic error, you can remove it. That's the nice thing about systematic error. And what you remove it, you lower your surface of the LiDAR up and down until it meets the ground control elevation. So you don't have to reproduce the data. You just change the header of the tile, or whatever you do, you z bump the elevation by one value, which is the amount of the mean, zero 0.2, for example. Once we do that, you look at the far right column, you see when I remove that, the debias data, the mean went back to zero. That's what you wanted. And the standard deviation stayed at 0.96, but the root mean square error becomes similar to the standard deviation, 0.095. That's the beauty of understanding these statistical concept. That's what you need your staff or yourself to be versed about, so you can do this kind of treatment without reflying the project, for example. And that's what you see here when I do profile in different section. That's what I saw always. The red is below the green by around 2/10, and that's what it draw my attention to the biases here. And if you want, here is I will give you a couple seconds if you want to scan the QR code for the download the PDF, which is a free, or if you want to order the hard copy, is beautiful. I love the hard copy. I have it on my desk. I use it all the time. Much easier than going to the computer and searching for things. And it's only ASPRS selling for $20. It's a beautiful production book, nice book, really. I encourage everybody to order that $20 hard copy standard. And with that, I think that's all I have here. This is my code, QR, my business card. If you want to scan it and store it, if you need any question in the future or help, I am here. I'll be happy to do that.